Hey, welcome back to Math with Patrick. Today is July 5th, and we're solving problem number 186 from the Daily Epsilon calendar. Looks like we have some information about y and z. We have three different bits of information, and hopefully that's enough to either figure out what y and z are, or maybe we'll just isolate their sum, y plus z, and we should show that that equals 5 today, which is today's date. So right here, I see that we're taking y and z, square rooting both values, adding both of those square roots, and we're going to get the number 3. And this tells me that y and z are like fairly small. Like if I tried doing like root 1 plus root 2, that's like about, well, it's exactly 1 for the square root of 1. And then the square root of 2 is about like 1.41. And so doing root 1 plus root 2 gives about 2.4, let's say, which is fairly close to 3. And then if I do like root 2 plus root 2 with that approximation of about 1.4, this will give me 2.8. So I'm getting like fairly close. So y and z are probably around 2, maybe like 1's 1 and 1's 3. Essentially, they're going to be pretty small numbers. It's also entirely possible that they're not whole numbers, and I'm pretty sure that they aren't, because as I'm trying with these whole numbers, I'm getting these decimal answers, and this result here is a 3. So maybe I'd need some like really unique looking numbers under here to actually get this first equation to be true. And in the next one, we are adding 5 to y, adding 3 to z, square rooting both of those values, then adding those together, and we get 5. So kind of interesting that we get 5 out of this whole mess, and we're supposed to also get 5 just when we add y and z together. Maybe that makes sense because like adding 3 makes numbers bigger, and then square rooting them usually makes them smaller. And so it would make sense to make these numbers both bigger, then both smaller, and then we get 5, and it would be the same thing as if we just added it to begin with. Lastly, y is strictly greater than z. I don't yet see why this condition is important, because maybe why not make z greater than y? Or maybe this is why it's important, because maybe there's another solution out there where z is greater than y, and then this sum isn't 5. Or maybe there's another solution out there where z and y are equal, but then it doesn't kind of satisfy this idea of adding them together and getting 5. And to be transparent, this was my first idea of what to do here. The opposite of square roots is squaring. And so I figured, why not square the first equation, square the second equation, and just kind of follow the algebra rules. And I got maybe somewhere, like I was able to get this y plus z in both my equations, but then I have this other term here that kind of clouds the information from me. So I can't really quite determine what y and z are yet with this strategy. Maybe there's a way to do some kind of system of equations here. But then I had a thought. This is really complicated. And instead of doing all of this, why not do a little bit of skillful guess and check like I was doing earlier? If we start with the 3 and think about, well, what plus what is 3, ideally I would just do 1 plus 2, or 2 plus 1. And the reason why I'm switching it around here is because y is bigger than z, so I'm kind of setting myself up for success right here. And I thought, okay, well, clearly 2 plus 1 is 3, so if I just kind of decide that this value might make sense, I could see what y and z have to be. And, well, the square root of 4 is 2, and the square root of 1 is 1, like we established earlier. So this at least satisfies the first equation. We should also make sure that this satisfies the second equation. So if we plug in y right here, we'll get 4 plus 5 underneath the square root sign. And if we plug in z right here, we'll get 1 plus 3 underneath that square root sign. And we should check whether or not this is equal to 5. Well, we get root 9 plus root 4. The square root of 9 is 3. The square root of 4 is 2. So this actually totally does check out. And then, indeed, 4 is greater than 1 because, if you count, 4 is greater than 1. And that's important because it then does satisfy the third condition. So ultimately, just a little bit of guess and check, honestly, is all we really needed to do for this problem. Because then once we plug in the 4 and the 1 into this equation, we get, well, x is equal to 4 plus 1, which is 5. So one more thing I'm curious about is like why we really needed this last condition. Maybe I'd be able to figure it out by doing something with the algebra here, but I'm just going to decide to plug it into Desmos and see what happens. Looks like we got two curves. One of them, both of them just kind of stop abruptly. Oh, wait, these look like they're arcs of circles. Maybe? I actually don't know. But anyways, actually, let's test that theory real quick. I could try placing a circle maybe at like 9, 9. Let me see if that actually works real quick. So there is kind of the center point, and then the radius should be about that. Okay, so I just plopped that purple circle right there just to compare it to the red curve. And so these curves that we have on the screen probably aren't circles, but it at least kind of looked that way for a sec. Anyways, so we do have the solution that we found right here. This 1 represents z being 1, and then this 4 represents y being 4. And so it looks like we do have another solution somewhere here-ish. And normally Desmos lets me like click on intersections to figure out their values, but for some reason it's not letting me here, maybe because these equations are like a little strange. Ultimately, with a bit of algebra, and by a bit I mean like a lot, I was able to kind of reduce the system of equations down to a system of two parabolas. And at this point, I knew I could solve it. So we still have the 1, 4, and we still have this kind of weird number that doesn't really quite fit with anything. But once you have two parabolas, you can set them equal to each other and figure out a third parabola whose x-intercepts are basically, they match the intersection points of the two parabolas from before. So I'll just delete those. We already found the solution of x equals 1 or z equals 1 back in the problem on the calendar. And so this factor right here kind of covers that bit. And then once you kind of know one of the roots, you could figure out the other with factoring. To isolate the other z solution, I would just take this factor and set it equal to 0. Ultimately, we would get, well, on Desmos, it's x equals 169 over 64. But for the calendar problem, this would be our other z value. And we could plug it into either of these parabolas at this point, and we can see what our corresponding y value would be. And this little button right here helps convert decimals into fractions. So we could have this as our z value and this as our y value. And this, of course, is greater than that. So there is another solution out there that would satisfy that system of equations, that the first two conditions in the calendar problem. But then we did need that third condition, because if we added these together, we're not getting the number 5 at all. This is a little less than that. So looks like that's why we needed that third condition there that I was a bit confused about at the start. But that's the whole problem. That's as far as I want to go. I mean, I investigated way more than I needed to, but I was curious. Anyhow, thanks for coming along. I'll see you tomorrow. Bye.